Okay, I see the record button. Okay, so I'm just gonna give a little introduction on floating point. Let me stop annotating so I can skip through the slides. All right, so floating point arithmetic has actually been around for a very long time. I found this out last week. It's been around since like the 1930s on the first mechanical computer. This was not an electrical computer. This is the Z3, which was in the 1938 or something. But the reason why this started is it is really sort of intuitive for scientists. We have scientific notation, right? We all learned this in grade school. If anyone didn't, feel free to let me know now, and we can go over that. But I kind of want to have this motivating example of 1/10, which would be 1 times 10 to the negative 1 in scientific notation. But in order to get, like how would we do 1/10 in floating point? But in order to get there, we kind of have to talk about a few things. First off, basically the de facto standard all throughout the world is the IEEE 754 standard, which is, you'd think it's kind of this stodgy old standard, but it's actually been revised in 2019. So it's still like an active thing that people research. In fact, there's a conference on this standard that happens every year now. It used to not every year. I think interest is increasing. So get in while it's still hot, I guess. But basically, this relies on the fact that you have any real number, you can represent it as the sign s times 2 to some power times a mantissa. And I'm going to be using these notations throughout, and this would be S, E, and M. So, okay, this is where it kind of breaks down. I love the program Tixi, but as I started to make this, I realized it's really just this laborious process. So I'm going to do an annotation here. So the way floating point works is it is an approximation of the real line. So let's have this green line be the real line. And we have negative infinity on this side, which is not a real number in the real numbers, but in floating point, there is a negative infinity and infinity. And then we have, of course, 0 at the center. But with floating point, there is a +0 and a -0, but don't worry about that too much. But we can think of, we have numbers between 0 and 1, 2, and I will only go to 4. I promise you're not going to see me drawing. Let's see if I can count.
Something about Sam's voice.
Oh, can you hear my voice fine?
Oh yeah, sorry.
Oh, okay.
I just brought my laptop near Dewey's and it did a weird thing. So
yeah, no problem. I don't understand the echo of that. My roommate. Anyway. Yeah. So we have 4 and so on, and what these form. I'm just going to do 1 to 2 and then 2 to 4 because they're kind of special. Or sorry, between 0 and 1 is kind of special. These are what are called binades, and what this means is all the numbers are the same. I guess I can, apparently you can do text on this, but I'm already drawing. This means each number is the same distance apart from one another, right? So between 1 and 2 and between 2 and 4, every single number is sort of the same distance. And this happens for every power of 2, right? So you can imagine between 4 and 8. And what this means is as you get further and further away from 0, larger or smaller, the numbers in between each floating point gets further and further apart. And this is a result of how the format is done. Okay, so I want to clear this. Are there any questions on this binade thing before I delete the drawing? Okay. So let's move on to a slightly nicer one. So anyway, so we have these that's just sort of a background a little bit to how floating point works. And the larger number you get, the less precise it is because you have this limited number of mantissa bits. So the next thing we'll talk about is rounding. So let's take each of these lines, these vertical lines, to be a floating point value. And anything in between is a real number, but it is not representable as a float. You just don't have enough bits. So you can imagine we're way zoomed in here. This is not between -1 and 1. This might be between some very small number. So we have some number x we want to represent as a float. And both of those up and down are considered faithful roundings depending on your rounding mode. And the closest one is obviously the one on the left. But then you'll notice there's this dotted line here, which is like the middle, in which case if x was in the middle exactly, it wouldn't matter. They're both equally far. So keep that in mind. And there's actually 5 different rounding modes to IEEE. I personally have never used more than one, and probably the same with all of you. You have to specifically set the rounding mode to be something different. Actually, has anyone used a different rounding mode? I would be kind of surprised, just because they have very, it's supposed to be sort of transparent, like you shouldn't have to worry about it.
So how do you switch between modes?
They are typically compiler. They're compiler like pragmas, not pragmas, but functions you call. So I think it changes based on compiler. With C, I think it's in math.h, you can set the rounding mode, for example. And it can be done dynamically within the program. It has some performance overhead. So basically with the ties break, so the thing I wanted to talk a little bit about, going back to the previous slide, is this tie breaking. What you do is you look at the final bit and make sure if it's equidistant, you have the ties break towards having a 0 at the end. And basically what that means is you're getting this rounding that is not biased, in the sense of it always is 0, but that might be bigger or larger. And so if you're starting to add up a bunch of things, it tends to average out to be like no rounding, or rather even. All right, and so now that we have these rounding modes, we can kind of get this model of what error looks like, because as we saw 2 slides back, you can't exactly represent all real numbers. You have to make an approximation. So given, and this is a little bit of a weird formalism, but just imagine this dot, this little looks like a bullseye kind of, is any operation: plus, multiply, divide, square root. Well, square root would be unary, but add, subtract, divide, multiply, your elementary operations. And you have this basically this offset, or rather this error term, the e. And I have a little mistake there, that e should be in absolute value. It's less than some epsilon, and this epsilon is dependent on the floating point format. Throughout this, I'll be using double precision, or be talking about that, just because it's just for consistency. So for the double precision, it's 2 to the -53, or a little bit more than 15.
Can I ask you a stupid question?
No stupid questions.
Okay.
There are no stupid questions, so ask away.
Is E? Like,
no, it is not. So E is just some number. E is not Euler's constant. E is just some value. It stands for error. So you can imagine this being like an example. E would be might be 10 to the -18 is an example E that would be valid, because that number is less than 2 to the -53. And so if you get, I guess if you get one takeaway from this presentation, is that if you're working with double precision, you can get about 15 digits of precision. Beyond that, you run out of bits. So And this is because 2 to the negative 53, if you take it in base 10, it's about, it's about 15 point something.
Sam, you may want to not use E, since E is sort of, you've already overloaded it twice. You used it as exponent in your first or second slide, and now you're using it as
yes, I see.
error. And then it's also thought of as the Euler constant. So maybe a couple of new terms might be useful.
Right. That is a good point. But alas, I'm not going to recompile for this presentation.
No, I don't expect you to.
No, I know, but I apologize for that. There's too many E's around here. And also epsilon looks like an E, kind of. So for sort of another thing you might hear is you might have this described as units in the last place. Because when you're dealing with these numbers 2 to the negative 53, it's sort of inconvenient to work with. So you can measure as like the number of units in the last place. And I have like I guess like a kind of not a pop quiz, but just like a question to check understanding, but I'm not sure if this is a good question or not. So let's go back to this slide here. And so if, all right, so if we have some faithful rounding, and or rather, let's say we have the rounding mode, which is round to nearest. And this would be this is a ULP. How much off is your approximation going to be from the floating point value? So again, I'm asking the question to the audience of, if we are doing rounding to the closest thing you have, rounding to nearest, how many units in the last place will you be wrong by at most?
Half of one?
Hit 2 power 53 at most.
Yeah, so someone said, I heard somebody say 2 to the negative 53, and someone said half ULP. The answer is half of a unit in the last place, because you notice this here, this dotted line is at 1/2 of a unit in the last place. So if you pick the closest rounding mode, you're never going to be half away from the closest number. So yeah, and but if you pick any rounding mode, it can be 2 to the negative 53 or 1 unit in the last place. So this is like actually kind of a very strong standard, because you can sort of think like, and you can imagine if you're doing floating point with floating point, you have these like hidden, you have these bits you can't represent, and you're expected to get this right. And so if you have this this property of you always round with it, you're always within half of a unit in the last place, this is what's called a correctly rounded. And the details of that I don't want to get into too much. I mean, I kind of already did, but the gist of this is that this is something that math libraries spend a lot of work on, or Intel hardware designers. They worry very much about the fact that these are correctly rounded.
So what's stopping you from having 2 of those dotted lines so that you can get it to 1/3 of ULP rather than, like, apart from the fact that it's more data, but like.
Right, and so the question was, what's stopping you from having it even better?
Yeah.
Well, the reason why is, let me, sorry, I gotta keep annotating to, so if, the example would be, what if we had something here, and then we could actually round to here? This would be a closer approximation. This would require 1 more bit of the mantissa. And so we don't have that many bits. This is sort of like all you get. If you have a floating point value here and you try to go 1 higher, the next one is up here. There's like this space here is like, in some sense, terra incognita.
Oh no, so that's why I said like you have 2 of those dotted lines, 1 over here and 1 in the center of the right side, so that you can split the error by 1/3 rather than 1/2 of ULP.
Oh, I see what. So you're saying have something
here, and then
like
have something over there on the other side.
thirds like this.
Yes, exactly.
Okay,
You can round
right.
up.
And so that's getting to I think so. Doing this sort of analysis, you could do this if you were dealing with like a ternary number system, but the fact is that these are binary, and so I don't have a good answer for this other than like you can really only round up or down. So this problem of deciding on which side of this of an arbitrary number I'm on, this is actually like you bring up a very interesting or rather challenging problem, because it's hard to know how close you are to this like inflection point, right? Because if we have some number, let's say right here, like very, very, very close to the center, if you're running something to compute it, you might switch back and forth very, very rapidly to say, do I round up, do I round down? And this problem doesn't get any better if you use, you know, 2 different points instead of just 1 point. It's still there. And so
I think there's a bigger problem, right? Because the dotted line it doesn't really exist, right?
Yeah, it doesn't exist in floating point.
So having 2 dotted lines that also don't exist makes it hard to tell where you're at.
Right.
So if you happen to be between them, how do you know?
Yeah, and so the way that most floating point do this is they have extra bits of precision they compute and then they round off.
Yeah, that makes sense.
And I think that this is getting into electrical engineering a little bit of how many bits do you need to do this. And it turns out you only need 3 extra little bits at the end to be able to figure this out of which direction do you round. But that is beyond sort of my area. But that's a good question.
If you're interested in that, you should take or audit computer architecture in the spring term.
Yes, and I've heard the TA is really good, or the teacher is going to be really good. Never taken a class from him, but I heard he's a good teacher. So I'll plug for that. This is actually where I took not a computer architecture, more of an applied one. This is where I first learned about floating point and really learned all the details about it. And I found it to be very interesting because there's so many subtleties to it. Okay. Are there any more questions? This is kind of a simple picture, but there's a lot of information crammed into it, I suppose. All right. Yeah, so we got it right. All right, so now, ooh, that did not look how I wanted it to, but imagine we have 1/10, and we're going sort of answering this question of how do we represent 1/10, and it turns out you can't exactly, in the same sense you can't exactly represent 1/3 in decimal because it's a repeating fraction. It's the same for 1/10. So imagine this 1/10 is to the left, and I just have the little frac messed up. So we have just this repeating binary representation. And this is what it looks like, the second bullet here. And you have this, right? We have the sign, which is the +1. We have the exponent, which is -4. And we have the mantissa, which is just this repeating fraction that you end up truncating or rounding correctly. So the error of this 1/10 versus the binary representation of 1/10 is at most epsilon, the difference of the relative error, but I haven't calculated the error exactly. I don't know exactly what that number is, but we know from this previous equation is that the error is at most epsilon, 2 to the -53. So this equation 2 here is a pretty good approximation of what floating point error is, but there's another wrinkle that I'm going to talk about that is a little that's more complicated, and that's called subnormal numbers. So with floating point, there's always this implied 1 at the beginning of your fraction, because if you have some number that is non-zero, you know there's going to be a 1 somewhere in there, because otherwise it would just be all zeros and in the mantissa. So this is what a normal number looks like. And I have this, this is like sort of a refinement of what I previously had. So we have normal numbers, which are a sign times an exponent times 1 point mantissa. But then if you have this subnormal number, you have a 0 there. And this is to represent like very, very small numbers. So we have this, and then if the exponent is all 0, it's some fixed, very small exponent. For double precision, this is 2 to the negative 1022, which is about 10 to the negative 300. To give you an idea about how small that is, there are about 10 to the 150 atoms in the universe. An atom is about 10 to the, I think, 10 to the minus 10 meters wide. So this sort of number, it seems like so ridiculously tiny that it is not ever used. And in a lot of cases, this is correct. This is like subnormal arithmetic is a lot of times put by the wayside when we're dealing with error analysis. So the thing with subnormals is you get less precision. So if we recall this mantissa, there is a 0 point, and this, again, this is in binary. I didn't put the base here, but it's a binary decimal representation. You have all these zeros, and you finalize with a 1001. We only get 4 bits of precision there, because you don't know what happens to the right of that 1. We ran out of bits. Just draw this here. There's no more bits. Everything to the right of this was already used for the rest of the floating point number. So we like are running off the cliff of precision. Things like GPUs, last I checked, they do not support subnormals, because you can think of the original use case of a GPU was to show a picture on a screen, and humans can't really perceive beyond like, what is it, 32-bit color or maybe 64-bit color. So if you're drawing something on the screen that lasts for 1/60th of a second, subnormals is just a complete waste of silicon to work with. However, there are cases in which it does matter that you get these subnormals right. So this messes with our error for things that aren't addition or subtraction. Now, when you're reading the literature, or you might see things like what every computer scientist should know about floating point arithmetic, you'll have these things that describe the, sorry, I keep switching back to the equation, but this equation 2 here. Because it's a very good approximation and it's relatively simple. However, we have to, if we want to be truly correct and actually cover all the cases of floating point, we have to add in this additional term. And I actually did remember the absolute values here. So we have this D term, which is D and delta, and this represents the error from subnormal arithmetic. Now, for addition and subtraction, this error is nothing. You just don't get error from it. But for something like multiplication, you can get this error. And typically this number, right, is much smaller, so it doesn't factor in. But for subnormal numbers, this number starts to be more important and actually significant, the main cause of, or not, it can be a significant cause of error. So really, if this is the actual, this is a pretty good model of what actually happens for floating point arithmetic. The reason I say pretty good and not an exact model is floating point does a little bit better of a job as number 5 because of all this business I talked about correctly rounding. So most things that you encounter are correctly rounded, which is not easily expressed in an equation, but you have a couple extra cases where if this happens, then your error is less. But for now, this is certainly an over approximation of what happens. That is to say, there will never be a case if a floating point implementation is correctly rounded, will the error be worse than this sort of expression given here with the epsilons and the deltas. Okay, so what are the implications of ignoring these subnormals, which a lot of literature does, and yeah, so what are the implications of this? Well, and I already used this example, but it's not a big deal, which is why people do it. I'm not saying this is a big crime, that everyone is this a grand conspiracy to unlock, but this can have issues when the cost of under approximation of an error is very large. So I think I have an example here, and you can see, I mean, this is not because of floating point, but one can imagine the case of, this is to distinguish between under approximation and over approximation. Under approximating how tall your truck is can lead to this sort of situation. Whereas over approximating, that you just have to, if you over approximate how tall your truck is, you would have been able to make this clearance, and instead you have to take a different route. But if you think you're 11'8" and you're actually 11'8.125, you will scrape and cause damage. So this is, I don't know, I'm sure there are better examples in the real world. I didn't have time to collect one, excuse me. But if you're interested, I can find some, and I have them, I just don't have them off the top of my head, where this actually does matter for a floating point. So do I have another? Okay, I'm gonna talk about this example where actually there is this case where the authors were very careful to over approximate the error of a floating point operation. And sorry, I just see that there might be some chats. I cannot see the chat right now, so I'll get to those later. But the one example would be this so-called sphere packing problem. And the question is, what is the most efficient way to pack a bunch of spheres in a three-dimensional space? This is one of these problems, these very famous math problems that intuitively, the intuitive answer is the right one, which is to pack them in this pyramid shape. One thing I want to note, I really like this annotation feature. I'm going to just keep using it. Oops, this is a triangle here. This is not a four-sided pyramid. So it's a triangle up here, and then you build up the spheres up from there. So this was proposed, I believe, in the 1600s, and it was finally proven. This is in fact the right most efficient packing in 2005. Rather, it was submitted in 1998. They checked the 3 gigabytes of computer proof or binary files or something like that for 7 years and accepted this proof. And I read a little bit of the paper. It tended to rely on this over approximation. And the fact that if you do different rounding modes, you round your floating point and you will never be less than what the true value is. Now, one might have difficulty calling this a very real world example but mathematicians hold a very high standard of what would be considered a proof. And so using this, this was a big step for computer proofs, because it meant that we can sort of trust computers to do some math for us, given that we're very careful about floating point. And actually, so this proof was proven in 2005, and then it was proven again in 2017. It was formalized in a theorem prover called Isabelle. So it's another application of using a computer checked proof to prove a yet unproven theorem. And I'll switch to the author list here. It's kind of interesting because there's a huge number of authors that worked on this project. One of whom I'm actually working on is collaborating with slightly for my next paper. So that was kind of exciting or interesting to see his name there. All right, so I'm going to go back to a little talk about why we might sort of care about these minutiae of floating point details. There has been a trend in the last 10 years or so with the explosion in machine learning popularity that they kind of want to get every last bit of performance or accuracy or useful work done out of the silicon they get. So it used to be the case that there was kind of only one floating point around, but now there are other things such as bfloat, which I think has more bits for an exponent. There's another number scheme called a posit. And I have a joke here, all of them heresy. This is not true. It's just I don't know them very well. Really what this is, I mean to have a positive tone here. It's sort of an exciting time for this sort of area because there's a lot more room for research and how can we most efficiently use these little floating point formats that on one hand it's bad because now we have to think about it, but on the other hand you've always needed to think about it. You could just get away with it a lot of times. So some of the very subtle bugs in programming can be because of floating point error. And I'm sure all of you at one point or another have done something in floating point and been confused because the real arithmetic held and the floating point did not. I know I have many times. Okay, and so that is basically the end of my talk. Are there any questions or follow-up? Maybe if somebody can, if the chats weren't already answered in the chat that I can't see, somebody can read them to me.
I don't think there are any questions in the chat, actually.
Okay, cool. Yeah.
On an unrelated note, like why does the pyramid 3-sided actually? Wouldn't it be more if it's 4-sided? Like,
one would think that. I looked at it and there are actually two configurations of which are the most efficient. And I believe one of them ends up looking like a 4-sided. It depends on what angle you're looking at it at. I looked and I tried to find a simple answer. I just, why not 4-sided pyramid? But you can think that the reason intuitively why the 4-sided one wouldn't work. Let me do my fancy little annotation again. Oh, can I do shapes? Oh, I can. This is great. Right. So if we have oh boy, that's not gonna look worse than I thought. If we have a 4-sided pyramid, intuitively we think something like this. Right, and we have all this empty space around in between. Whereas if you have a 3-sided pyramid, you can kind of fill that with in between here. Sorry for the sort of not great drawing, but I think you kind of get the idea. There's this 4-sided shape inside, and you can pack them closer by shifting them. It's a pretty interesting problem, sphere packing. If you want to look, the Wikipedia page is pretty good on that. But yeah.
Any other?
I had a question.
Mm-hmm.
Go ahead.
So like you mentioned that like recently there are a lot of like new innovations in like standards that they can use for floating point numbers other than the IE 754. But if like people weren't using that, would it really just like the only way to work with subnormal numbers, would that have been to just kind of pray that the error just kind of evens out over
Yeah.
your data set?
That's a good question. So like for example, let's take graphics GPUs. You hope that the error is sort of biased either a little bit negative or a little bit positive, and it kind of evens out, and you don't need all those digits of precision. And usually that's the case. The other thing would be you have to update a little bit your precision to say for very small numbers, this thing might just flush to 0. And for something, I believe that like a B float, I think it stands for brain float. I don't think that they have subnormals. And in which case, you have these, basically what you're getting is you're getting things that are more likely to be 0 if they're very small. And I believe for a lot of use cases of machine learning, that is totally okay, because you don't even really care beyond a few bits of precision, much less all the very smallest ones. And so it's what it is. It's a trade-off between how much precision do I get versus how many operations like per silicon, or per clock cycle can I get, because subnormal can really slow things down. And you can actually, I believe with GCC or something, you can turn off subnormal arithmetic, which typically won't have a performance impact, but in some cases it may. So, yeah.
Thank you.
Yeah, of course.
Well, thank you. Virtual clap.
Thank you.
Thank you.
I'll stop sharing now, and
I can stop recording.
great.